Hello everyone, I am Sara Saberi and I want to talk about our article entitled Wavelet-Based Generative Adversarial Network for Texture Synthesis. Problem definition. The main issue of this article is changing the texture of an object to the desired texture so that the new image has the visual characteristics of a real image. That is categorized in the image-to-image translation and computer graphic fields. This problem can also be defined in the form of texture synthesis, which means that by having the sketch of an image and a patch of a desired texture, the texture can be spread throughout the object to maintain its authenticity. The importance of the issue. Texture synthesis have various applications in many fields such as image restoration, editing, compilation and retrieval, video compression and synthesis, making the animations, material simulations on 2D, 3D synthesis, customization of products in the online stores. One of the most important challenges in this area is the production of high-resolution image because the texture is the result of change in image details that must be high-resolution to represent. First, we review the recent prominent research in this area. With the significant development of deep neural networks, image-to-image translation has become a widely used field in the world of computer graphics. Topics such as edge-to-image conversion and vice versa, image compilation, satellite image to map, and image colorization, transferring a style, texture, or domain are among the most used topics in this field. In recent years, generative adversarial networks, or GANs, and their variants have become the state-of-the-art solution for these issues. Generative adversarial networks were proposed by Goodfellow and al. In 2014, which the learning mechanism is based on game theory, and you can see the objective function in this formula. As shown in figure 1, they have two networks, a generator and a discriminator, which can have a convolutional or fully connected structure. The generator network tries to create fake but acceptable images, while the discriminator tries to distinguish between fake images that produced by generator from real images. In general, generator G maps a noise vector Z into the feature latent and reconstruct it to make an input image, and then discriminator D must classify this image as real or fake. GANs are categorized in two major families, unconditional and conditional. As shown in figure 2, in conditional GAN, the production of images have been done under certain conditions, such as class type or special visual features. These conditions are provided by the error statements defined in the network objective function. One of these types of controls is done through the edges of the input image and its texture or style features, so that the output image must retain exactly the content of the original image, but its texture or style is similar to the user-defined texture. For example, Zhang and al. Proposed a generative model for real-time coloring of images, which consists of two branches with different inputs, gray image and user custom colors, which are combined with the content properties in the color training path. Or in this article, Sankloy and al. Use sketch and color to control the generated image. The structure of the generator network is an encoder-decoder network that the input image is downsampled 3 times and then taken to the feature space using 7 residual layers. And in the next step, the feature space upsample using bilinear method and residual layers goes back to the original image dimension. And in this article, Jean and al. use the edges of the image aligned with the input texture as a condition to control the generated images. But the images produced have a low resolution, which makes the texture details not produce well, and the edges are not enough sharp. Also, the new texture doesn't spread throughout the object. And our proposed article tries to solve these challenges. Wavelet transform. Wavelet transform has become a powerful tool in image processing due to its ability to describe images at several resolution levels that are similar to the human visual system. Typically, the wavelet transform maps an image on a low-resolution image and a series of detailed images. The low-resolution image is obtained by iteratively downsampling the image. The detailed images contain the information lost during this operation, which the energy or mean deviation of them are the most commonly used features for texture classification and segmentation problems. Many researchers use wavelet packet decomposition in texture analysis and synthesis. For example, in this article, the proposed GAN model is based on wavelet coefficients, in which the generator network predicts wavelet coefficients of low-resolution image, and the discriminator network is responsible to identifying real or fake for them. So, the generator has been trained to generate exhaustive wavelet coefficients that lead to improving the resolution of the reconstructed wavelet coefficients. In our proposed method, model training is done in 2 stages. In the first stage, the ground truth image is available and the generator must learn to reproduce it by having the sketch and a patch of the original texture. In the second stage, we don't have the ground truth image, and the network must be able to learn the new texture and spread it throughout the object. In this stage, we fine-tune the network with changing the input and ground truth images. The structure of the model in the first stage of training is shown below, which is a subset of conditional generative networks. The conditions that control the generated image are defined in the form of loss terms, which are described in continuum. In next step, a local discriminator model is added to the network structure. Each time the output image of the generator is generated, a piece of it is cut and given to this local model to compare with the piece of the target texture. Objective function. Defining the objective function is a vital factor in the design of neural networks, especially GAN. In fact, the formulation of problem and the factor of difference in networks is called objective function. In this study, the purpose of the problem is converting an sketch of an object with a patch of desired texture into a real image with this texture. Therefore, a loss term was defined for each component of the problem and optimized in the objective function. As shown in below equation, 6 loss terms used in the target function with specific weights W. And feature loss, style loss, adversarial loss, pixel loss, color loss, and wavelet coefficients loss. Feature or content loss. Research in the field of style and texture transfer has shown that VGG pre-trained network can be used to extract features related to content and image style separately. The features that have been extracted from both the original and the generated image are used to calculate the feature loss. Layer ReLU 4 of the pre-trained VGG network 19 is used for extracting features. Then the distance L2 or MSE loss on them is calculated. The purpose of calculating this error is increasing the similarity between the content of the generated image and the original one. Style loss. Getty suggested a way to calculate the correlation between some feature vectors by constructing the gram matrix. This leads to a more accurate learning of the texture and image style properties. Therefore, to calculate the style loss, the gram matrix formation method was used on the feature space which extracted from the ReLU 3 and ReLU 4 layers of VGG19 model. Pixel loss. The result of calculating the L2 distance on the pixel space of the image generated and the grand truth. And adversarial loss. This loss is the main error in the learning of GANs that focus on producing more realistic images. For calculation of this loss, the error defined in conditional generative networks was used. The only difference was the use of least square error creation instead of calculating cross entropy. And color loss, the L2 difference between color of grand truth and generated images in pixel space. And wavelet losses. For this loss, we use the wavelet coefficients of generated and grand truth image. The wavelet coefficients are calculated in 4 levels by equation 3, once from the output of the generator network G, and again from the target image GTH. Then for each level, the error value is separately calculated by equation 2, using the MSE criteria. Finally, for calculated losses, LW1 to LW4 added together to obtain total wavelet loss. In this study, 2 datasets in the field of fashion were used in first stage of training. The first dataset is the BAG database, which contains 139,000 images, and the shoe dataset, which contains 50,000 images. For the second stage training, which is done as an unsupervised learning, new textures are required that were not seen in the first step. So we use the DTD dataset that includes 5,600 images of 47 types of textures from different classes. For implementation, we used a system with a 1060 GTX GPU with 8 GB RAM on PyTorch platform. The number of training epochs is 48, which has been done in 96 hours. The evaluation metrics. The FID criteria has been used in many studies to evaluate the quality of generated images in terms of similarity between real and fake data. To calculate it, features from real and fake images were extracted using a pre-trained inception network, then modeled using multivariate Gaussian, and the distance is calculated between distributions. Lower FID values shows the better quality of the generated images. SSIM has been used to evaluate image quality in some studies related to resolution enhancement and is closer to the human visual system in terms of visual perception than other evaluation criteria such as RMSE. Higher values of this criterion indicate that the data being compared have more structural similarities. Superior of our method shown in below table, and our generated images are more realistic than previous research texture GAN. Thank you for attention.